Okay, so we'll get started. The goal for today is to finish what we started last week, which was principal component analysis. We just started motivating it, and I'll try to finish it today because this is kind of like the last lecture in some sense. The next lecture, of course, Friday is a holiday, and on Wednesday we'll have a guest lecture coming and talking about risk modeling for cancer. So I'll announce this on Piazza. He's a visiting faculty at KCDH. This is kind of, in some sense, the final lecture. We'll again meet on Friday where I'll go over if there is anything remaining from today, and we'll review the course. नहीं लगेगा कल भी एक्चुअली लास्ट टाइम भी नहीं हुआ था तो मैं उसी स्क्रीन पे आ रहा था सिर्फ हाँ एक मिनट इधर आ रहा है नहीं ये लास्ट हाँ अभी आया ओके ओके थैंक यू थैंक यू थैंक यू Okay. So before I begin, actually, few things. So sorry, I think I should have started with an apology. I posted an invitation for the workshop, the GitHub workshop, and I had a different idea in mind when that workshop was planned. And those of you who came, I don't know about you, but I felt the term workshop was not something which was heeded to in some sense. So apologize if you ended up wasting time. I will have to be careful in inviting people to do this. But the only thing I can promise is next Wednesday when you come in for the guest lecture, that will be full of content. Okay, that there is no doubt. Okay. Also, it's interesting. So I somehow sometimes a lot of it's done to check list the mandate that comes from wherever from the top, and it somehow flows through. And this morning I got a request to post about it on LinkedIn, right, which of course I did not want to. In the process, actually, I discovered that one of the class slides has made it to LinkedIn somehow, which is great, which is always good to see. I will let you figure out which slide that was. Okay, we'll talk about, first thing that we want to talk about is actually course projects. We are warming up now. We have covered a lot of analysis, and we have done some fair bit of methodology, including what we're going to do today. So the course is of 30% weightage, right? So in the sense, it's right now, it's actually, it carries more weightage as compared to what we have covered so far, which is ballpark 20%. 20% we have covered so far, including the assignments and quizzes. 20% will be mid-sem, so 40% up to mid-sems, 30% for course projects, and another 30% for the portion that Nirmal is planning to teach. Right, so this is going to be a course group project, so there'll be a team of 3 at max. The idea behind these projects is to apply the principles that you learned here to do some interesting stuff with real data, right? This real data will come from not simulations, not like synthetic data, but actual measurements that have been done out there. And I've put down a list of last year projects. This particular document also has some sources for data that you can use to think about ideas. But how do you think about ideas? The idea behind the thinking that you should do is disease X, whatever that disease is. It's, these are like ballpark ideas. Of course, you're welcome to think about anything, and I'm just giving you ideas from my perspective, so don't get biased. You will have ideas, right? You will, of course, have things about, like, for example, things that we talked about in the class about births and being related to marriages and so on, or being related to agrarian society versus monsoons versus whatnot, right? So we have discovered, enough questions in this class over this period that will make, as long as you're curious, you will have those questions about how does this happen in India, right? So, for example, I don't know how many people die in India because of cancer. That's a starting point. Is the amount of incidence of, let's say, esophagus cancer or colon cancer similar across different states, right? Is it different? Is it different? Why is it different? So those kind of questions you can ask. There is enough data to help you actually understand this question. It's severely under-analyzed. Like, a lot of data in public health domain is severely under-analyzed. So there is a lot of room for you to actually come in and think from a very first perspective. You don't have to be a public health person to actually answer these questions, because you have that methodology and the engineering mindset which is often required for solving this problem. I'm not saying that we'll solve all the public health problems, but the idea behind there should be, can you bring the focus, can you bring your ideas, and can you show that there is often a gap which has so far not been characterized. That's what the central idea of these projects is. You can do disease outbreaks. You can develop statistical models for detecting diseases. For example, if you have images, you want to detect cancer, you want to detect any other disease, all those broad ideas are all welcome. Any other question that interests you, that is broadly public health informatics or health informatics, right? And both these words hopefully now make sense to you. We understand what is health. We understand what is informatics. As long as the central domain is this, all ideas are welcome. So let me just quickly glance through last year's projects, so you have some perspective of what kind of things people worked on, right? So this is just from last semester. So one of the projects was about how gender, age, lifestyle, and health factors like BMI, stress, and physical activity influence sleep disorders, quality and duration of sleep, right? So of course you can come up with questions, but the second thing that you need to know is, do you have access to public data, right? All of this has to be from public data. I don't have any private data which I can share with you. Nobody else in this institute will usually give you private data, because everybody has their own life and their own research mandate to sort of go for. So focus on questions where you can find some evidence of public data. Otherwise, a question could be good, but if there's no public data, it'll be very hard to solve it. The second question was very, very interesting actually. This was evaluating Thailand's 2002 universal coverage mandate to assess its impact on health outcomes and system efficiency, while examining potential issues like moral hazard from increased healthcare access, right? So the central idea was, at some point Thailand decided to, it's doing very, very good actually in terms of its healthcare metrics. And one of the reasons it is doing it is it is one of those countries which has this universal coverage already implemented. So everybody has access to healthcare. And if you had data from before 2002 and after 2002, you could actually compare that with universal access. Has the disease burden gone down, or has the life expectancy gone up, and so on? And this is what I think this is broadly what the project was about. They did, actually, this was a very good project overall. I was not part of evaluation for all of the projects, so I cannot give you that perspective. I can just tell you about certain projects where I was part of the evaluation, because we have changed the way we do projects. Last time the project was more of a second half thing. Now this is a merged version of both the first half and the second half. Okay. Then, of course, you can do something with devices. So, for example, analysis of CGM. This is continuous glucose monitoring data for assessing diabetes management and public health outcomes. Like all these interesting questions, of course, but as long as you have access to this data, right? So, we'll put resources for, some of the resources are about where to get this data is already here, right? COVID-19, for example, contact tracing, analysis of life expectancy, all those are, of course, all welcome, right? So, I've already put some data here, data sources. We'll keep expanding this. But if you have a question and you're not able to find data, you're welcome to ask this question on Piazza. That I'm looking for this kind of hypothesis. Are there any public data sets? And I'll try to find it, right? I unfortunately will not have access to all the data that you have, but if it is in public, we can try to find it together, right? So these are some of the data sources. Just to give you a preview, NHA and ES is like the NFHS, which is a national, which is like a family health survey for the US. Very good quality data overall. Very again, something which is underutilized. Very interesting questions that you can ask. For example, one of the questions that you can ask is depending on which population. So in India, it's urban, rural. In America, in the US, it's mostly areas which are inhabited primarily by, let's say, black population versus others. You can think about understanding or characterizing what is a different disease burden. Is their BMI is different? Do they get more hypertension? Do they get more diabetes? Is it because of their economic status and so on, right? Like all sorts of questions that is possible with that particular data. You can also ask questions about births and deaths. It actually measures, it does longitudinal studies to characterize how births and deaths are happening. So very good quality data overall, very underutilized. NFHS, of course, is National Family Health Survey. What we worked with was the summary data, which you saw everything was in terms of percentages. You can apply, and I will strongly recommend if you want to work on India, you should go at this URL and apply for access. When you apply for this access, what it gives you access to is individual level data. So there are like 8 lakh people overall that were questioned for these different questions. You get individual level data. The idea behind those individual level data is you can do very interesting kind of analysis, right? So one of the questions that you tried to answer in assignment 2 was about, what was the question from NFHS? Yeah, exactly, right? So top 5 variables which explain the fertility decline, or which explain the fertility. You can bring in all sorts of, if you had actually access to individual level data, you could build models. A simple model would be a simple regression model to say whether decline in fertility is correlated with any other factors, right? So giving you access to individual level data allows you to ask very interesting questions in that sense. For example, you can ask questions about, a very simple question that, for example, you could ask is, what is the distribution of the number of children that happen when, or what is the distribution of the mother's age across different states when they have their first child, when they have their second child, and if they have more children, how does the age matter, right? So it's a very interesting analysis in itself. This data set has been out there for 3 years, but only very few people have actually been able to analyze all sorts of things. And one of the questions that I just said right now was something which just got analyzed in the last 1 year or so. A lot of interesting questions that are possible. There are 131 plus variables that you can actually try to ask. You can try to correlate one with each other, and this is one of the exercises that we'll try to do today. MCCD is medically certified cause of death data. So deaths that happen in the institutions, which is hospitals, primary health centers, secondary health centers, and so on. They get assigned a cause of death. Why did that person die? You get, so around 20% deaths in India are certified by this medically certified. You can ask questions about how are deaths happening. This is a longitudinal data in some sense. This will take you to one report, but there are reports from all the way from 2012 to 2022. You can, a very simple thing that you can ask is, how has mortality changed in India? Like why are people dying, or which cause is what people are dying more from now? what explains it, and so on. Like those are the kind of questions you can ask. SRS is your sample registration system. So sample registration system is where births and deaths get registered. This is overall a very high quality data, but you only mostly get numbers. So you cannot do just a project on this, but it could be a good resource for you to tell you to sort of help you understand how many births are happening, how many deaths are happening, what is, if people are dying, at what age group they are dying, and so on. Some of you will try to do disease prediction or try to do climate science and health intersection. So there's weather data, of course, also available. This list is not comprehensive. I'm happy to expand this if you have a question. But there is weather data is usually available for free if you have a question in mind. There are a couple of more data sets which I'm going to add. One of them is disease outbreaks, like how diseases, there are certain viral and bacterial diseases that happen. It gets captured in this portal called IDSP, Disease Surveillance Program. So which diseases are spreading in which areas, at what point of the, at what time of the year do they come in? I will add those resources. But start thinking about questions. That should be your step level 1, and then we'll think about data sets. Okay. The project overall will be done in 3 stages. These 3 stages are going to be, in round 1, you will submit just a proposal with your team members. What will be their individual contribution? I will talk about it in just a bit. This will be 5%, will be due on 24th September. This is after your midterms, so you have had enough time to think about the question, the team that you're going to make, and what is it that you're going to work on, what data sets you're likely going to use. Round 2 will be in person on 22nd and 24th. So the second half will be taught by Nirmal. Nirmal will not be able to join on 22nd and 24th, but those 2 classes we will convert to an initial feedback session where you will come up with your initial analysis, right? So once you give your projects, we will have an initial, we'll do a screening. Most projects will hopefully go through, but if there are projects where we think that that's not suitable, we will let you know within a week of this submission. And when we meet on October 22nd and 24th, each group will present for 10 minutes. What have they done so far? What are the questions that they're asking? What is the data source? And what is the model that they've developed so far? And finally, in round 3, which will be the final evaluation, you'll have a group presentation on 24th November, tentatively. This is after your NSEMs, where you will be judged for, of course, your group will be judged as a group. So there's a 5% 5% for report and 5% for group presentation, but there's a 10% individual component, right? That individual component is something which will come from we just asking about what was your original contribution and how much do you know really about these projects. I'm sure you've worked in groups, and in groups it's always tricky because there are always groups where one member contributes and there's always one member who never shows up. All of this will happen, but we don't want to penalize the entire group for that. So that's why this 10% contribution will hopefully motivate you, right? This is not to demotivate you, it's to motivate every member to contribute actively. Okay. Any questions from this slide? November 24th is after your NSEMs. 22nd and 24th are, of course, in class, and proposal is due on 24th, which is after your midterms. Okay, what is the expectation, right? So for round 1, the expectation is very, very simple. Just come up with a proposal, a broad proposal. What is the plan of work? What is the overall theme of the idea? What is the question that you're asking? What has been reported in the literature? What will be the source of your data? This will be due on 24th September. I'll talk about it in just a bit. In round 2, we will just do an initial round of making sure that you're not stuck because of data issues, you're not stuck because of model issues, and this will be the opportunity for you to tell the rest of the class what is it that you're working on, because we will not have that opportunity later on. And finally, in group 3 will be just your presentation, your report, and individual contribution questions. So this is round 1, which will be the most recent thing that you will work on. So there you will talk about, you'll basically be submitting a Google form which would look something like this. Your group, what is your group name? What is the project theme? What is the source of your data? What is the plan of your work? What are references? And you have 3 members, right? you have at max 3 members, what will be their individual line of working, right? So that is something that you're going to set up very much early on, so later on there is no confusion. Okay, it should say it should just say maximum of 3. Sorry, I will correct this, right? So this is because this is from last year. Okay, this should say maximum of 3 group members. Okay, any questions? So some of you will of course want to work individually, that is always welcome. Some of you might not be able to find a group partner. So once we come up with these initial list of ideas, we will open Piazza for helping you find a project partner. So what I expect there is, you just post your name, what is your broad interest, what ideas you're thinking, and I'm sure you'll find a match somehow, right? It's like just you're looking for partners which have similar interests. Some of you, this is a good reason to come to class because you can find out your partners here itself. But if not, we will help you. But I will not be able to or even Nirmal will not be able to put two people together. That should happen organically from your side. Okay. Okay. Any questions about the course project? Okay, in that case, we'll begin. Yes. Yeah. You can use any language. Yeah. So language is no bar. Yeah, I know it has caused a lot of heartburn for you from some side, right? Like because I'm forcing you to use Quarto. I'm forcing you to. Well, I was never forcing you to use any particular language, but my code was in R, right? So that is just because I will tell you why in just a bit. When you get your evaluations for assignment 2, you will know where Python goes wrong. But in any case, no bar on language, whatever language works, that's fine. The report, of course, should have all your details about what was the source of data and so on. For assignment 2, right, like I know some people suffered and, I'm very sorry about it, but think about running a class like this. It's not easy. If anyone, including me or the TA, has to run each Quarto Markdown notebook from scratch, that is impossible. We just cannot do it. We just don't have the bandwidth. At some point, we're going to automate some of it, but we are not ready yet, right? So that's why I require a PDF submission, and that's why we require it to look in a very similar format, which allows us to do it, right? So this is, I'm not forcing you. I'm forcing you because for a reason, right? To make everyone's life simpler. If that happens, you will get your scores like towards the midsem, which I don't want to do, right? Like usually you will get your scores within 1 week of your submission. So to ensure that level of production line, and this is a production line, right? That to ensure that level of production line, we require some minimum standards. So that is the minimum standard that you have to meet. Okay, that's why I will not take QMD submissions. Very, very simple. Yeah, question. Yeah. So you are welcome to, like if you want to do machine learning, deep learning, all that is available. Sure. Yeah, no restriction on sticking to what has been taught in the class, as long as you're solving a problem, right? So you're using the most fancy lasso regressor or the most fancy any other variable selection method or estimation method. All that is good, as long as you can explain how it works. No, usually I was in like the problem is health informatics. Some of it could be you might end up doing something which I or Nirmal have not even taught in the class, and that's fine as long as it broadly belongs in the health informatics. Yeah, if it's necessary, right? So no force feeding, right? Like nothing is being forced. Solve a problem, yeah. Like solve a problem, right? Like all that matters. Just solve a good problem. Yeah. Yeah, solve a problem, right? Like we're all, in some sense, we are here to solve some problems, right? So solve a good problem, content no bar, health informatics, right? So it cannot be, well, you cannot come and say that I proved this theorem for this class. I don't care, basically, right? So good for proving a theorem, but I don't care, basically, right? So it has to be realistic, real data, a relevant problem. It could be any relevant for you maybe, right? But something to do with health informatics basically overall. Very, very broad. The course is again not the end, right? This is a means to an end. So whatever you decide to do, all that is good as long as broadly is health informatics. You want to bring economics part of it, you are welcome to do it. Okay, but the data has to be related to healthcare, right? Can't be I am solving let's say plant biology problem, right? Like it's fine, you know, of course it's good in the field in itself is good, but everything has their limitations. Okay, any other questions? So we have a lot to cover today, but I think we should be able to do it. So we talked about this, where the goal was we want to reduce this dimensionality of this picture, and we thought about it in a restricted way. We say that, of course, I can reduce the dimensionality, but I want that dimensionality to be of certain, to have a certain structure, which is, the structure is that when I reconstruct this 2D picture, I want to retain as much information as I had. In other words, I want to minimize the reconstruction error. Okay. So the way we approach this problem was we came up with this random line, we projected each of these points, and we got this reconstruction or this new representation in one dimension, right? So what was required for me to retain 2 dimensions, I can now do it in 1 dimension. And the reason to think about these dimensions is because more dimension requires more information content. Our data set, which is National Family Health Survey, has 131 variables. 131 variables, too much data. We can't really visualize it. We want to see the structure of this data. We would want to work in a slightly lower dimension where we can at least visualize things, right? Or do some sort of interesting analysis there. That's why we are trying to do this exercise. So here, when I projected this, I would like to reconstruct this, and the only simple way that I can reconstruct this is just rotate it to where I began from. And that gives me a 2D picture. In the process, what has happened is, of course, that you've lost some information because right now all your data points lie along this axis, but to begin with, they actually were very, very different in some sense. Right, so we talked about vector spaces. This is not extremely important, but if you want to represent any information in any dimension, you require access to what's called a basis vector. That basis vector is something that is going to help you construct the space. For example, if you want to represent a circle, your basis vector is these 2 orthogonal vectors, because any point in this circle can be represented as a linear combination of these 2, right? Something that you have done, right? And it's not very hard to see that I can construct anything from these 2 vectors if I add one part and the other part of the other. So those are basis vectors for R2. You can think R2 means it's a real number space with 2 dimensions. You can, of course, think about this in higher dimensions, and that's what Rn stands for. And right now it will appear very abstract, but the moment I hopefully describe SVD, it will make sense why we're talking about Rn and R2 and so on. But any questions about this slide? Okay, fair enough. So we thought about being able to reconstruct the error, and this was your original point. When you reconstruct, this is the error that you try to minimize. Now, if you think about it, when we try to minimize this R, this point is almost falling onto this point, or other words, this point is very, very close to X. I can always drop a perpendicular from the original point to this line. This is my reconstruction error. This is my variance, right? Why is it my variance? Because this is variance of the projected point. Because all my data is centered, the mean is here is 0, and variance is defined by sigma of x minus mean squared. Here there is only one point, mean is 0, so that becomes my variance. Right? And essentially, what I want you to sort of take away from this particular slide is, if you want to reconstruct and minimize this error, it is equivalent to maximizing this variance. So minimizing the reconstruction error is equivalent to maximizing the variance of the projected data. So when you project and when I use that dimension, the reason I have chosen that dimension is because in this dimension the variance is maximized. Okay. So let's do a very, very quick example to give you the intuition of what is it that we are trying to do. So let's say I gave you this is again a data in 2 dimensions, right? This is x and this is y. I want you to give me a dimension along which the variance of the data is maximum. Which direction here has maximum variance? Maximum variance. Where? Here? Let's take some options. So what is your option? Okay. Okay. Any other options? But I think it's intuitive enough, right? If I ask you only for one dimension, you will see that there is so much going on here that the variance of along this dimension, right? No, I have not even done any projection, but of course you can do a projection and you will see that overall it seems that that will have so much going on there, right? Okay, this is one axis. Let's assume that we figured out that axis. If I ask you for a second axis from this axis where the variance is maximized now, which direction will that be? Yeah. Okay, that side. This one? Okay, why? Yeah. Yeah. Mm-hmm. Yeah. Yeah. So hopefully, this is what PCA does, right? Like PCA is not very difficult to understand. It's looking for those directions where in some sense your spread is maximized, right? So this in this direction is maximized. Once I've chosen this direction, in this direction it's maximized. So I can always run PCA on this plot, and if I ran a PCA on this plot, this will become what my plot would look like. I'm not doing justice, but this is your what's called your principal component 1, PC1, and this is your principal component 2. So you can always do a PCA, and I can always represent this in a new coordinate system. So very, very briefly, what the principal component is doing is just looking for the correct rotation of your coordinate system such that the variance along those directions is maximized, or the amount of information. Why variance? Because variance in a very layman term is a measure of information. How different things are good for data, right? You want to retain as much information is in there in the data, which was earlier in higher dimension, but now you can capture it in lower dimension. So this is essentially what is PCA doing. In this case, there's not much meaning because this is 2D and this is also 2D. But imagine if this was a higher order space to begin with, you would have captured as much information as possible in a 2D space. Any ideas about, if I were to ask you that, is PCA a linear model or not? What would you say? Is it linear or is it non-linear? Mm-hmm. Yeah. So from here also you can see, right, like at each point, all that I'm trying to do is I'm trying to look for that rotation, right? So there's no nonlinear operation that has happened here. This we will not explicitly cover, but how do you think about PC1, right? PC1 is nothing, but if this was X, okay, this is already X and Y. it's some combination of x and y. Similarly, your PC2 is some linear combination of x and y. Why? Because you can see from here, right, that this axis can be written, if this is your basis vector, you can write this as a linear combination of x and y. This again is another vector in this space, you can write as a linear combination of x and y. Right? So any principal component that you draw is actually a linear combination of your original space. What matters is what is your alpha, how much is it coming from one, how much it is coming from other. In very, very loose sense, what you're trying to do is, if any particular axis has more variation, it will have higher weightage, right? So in this case, x and y are kind of equalish, but if I rotated this slightly here, so more points were having more variance along the x direction, then my alpha will be higher, which means that more of my contribution is actually coming from the x side overall. So PC1, any PC can be written as a linear combination of your original components, right? It's a linear reconstruction of your original data. That's what it is. Okay. Okay. So that's how to think about this. Requires some discussion about what is a covariance matrix. So the covariance matrix, you have already seen what is variance, which is sigma of xi minus x bar square, and sigma over the number of points. The idea behind covariance is you have two different variables that you're measuring, xi and xj. The covariance is essentially a measure of how much does one variable inform me about the other one, right? So the formula is this. If you require formula in your exam, I will give it to you. Okay, so I usually don't ask questions which require formula. So if required, I will give it to you. I think this was a question on one of the Piazza posts, so I'm just clarifying this. So this is the formula that's given to you, right? But what I usually want to do is I want to figure out, okay, this is a formula, but what does it tell me? The formula is essentially a measure of that if I have access to x and if this value is high, it tells me how much can I predict y. That is what covariance is a measure of. So in this case, you have two variables, x and y. So what you get is a covariance matrix, right? So this is a measure of how much x is predictable from x. This is measure of how much x is predictable from y. And these are the entries of your covariance matrix, right? So E of x minus x bar, if I have to write this in terms of formula, this is basically equal to what? This is just variance of x, and similarly this is just variance of y. This is always going to be equal to each other because the order of this operation, of course, does not matter. So covariance between x and y is equal to covariance of y and x. That part is clear? Okay, so from here, right, let's just look at some patterns and see if the covariance pattern is 0.21 and this is 0, 0, what does the distribution would look like, right? So here, this is 0. That means however much I measure x, I will not have much to tell about what is going on in y. And you can see here why that is happening, right? So here, x can change in this direction, but y can be anywhere, like it's going anywhere actually. So even if I measure x, I cannot really tell you where is y going to be. And that's why these diagonals are 0. Now focus on these two numbers. Here it's 0.2, which is a measure of how much is the variance in x, right? And you can see it's very tight. It's very, very in this narrow domain. That's why this is a smaller number. You will not be able to predict what this number is, but you can predict the magnitude difference between these two numbers by looking at the distribution plot, right? So this is what the distribution looks like. So there is much more variation going on here as compared to here. That's why the variance is high. Okay. Similarly, you can have a distribution which looks like this. Now see what is happening here. Look at the values first of all on this x and the y axis. So here there is some variation, of course, happening in the x direction. That tells you what is the variance of x, which is 1. there is also variation that's happening in the y-axis, which is, it's not as discrete or as large as what you're seeing in the x space. So that's why this is smaller now. But look at what is happening between x and y or y and x. As x increases, my y is on a decline, right? So that's why the amount of information, while I can predict x from y, it's going in the opposite direction, right? Is that part clear? Like if I were to rotate this, of course, I will be able to see a very tight correlation, which will be positively correlated. But measuring x in this direction means y will go in this direction. That's why this is negative. Now, if that is clear, help me understand why this is like this in the third plot. Why is the covariance matrix for this distribution plot 1, 0, 0, 1? Go ahead. Hey, go ahead. Yeah. What happened? All good? Boring? Yeah, go ahead. Mm-hmm. Yeah, eigenvectors we have not even talked about, but we will come to it. We'll come to it. You're 2 steps ahead, but fair enough, right? So look at just this plot, right? Like if I look at this plot, if I measure x, again y can be anywhere, right? There's no correlation between x and y. It's like a Gaussian blob in some sense, that this is kind of all a hodgepodge, right? So even if I measure x, I will not be able to accurately tell you where is y. That's why this is 0. And kind of the spread here is between 1 and 1 and 1 and 1. So it looks equal in the direction. I am not asking you what this number should be, but the relative magnitude is something that you can predict overall, right? So that's why this is 0, 0. That is clear? Because you cannot go from 1x to 1y. You will see why I'm talking about this in just a bit. Okay. If that is clear, I'll just take one example here because some of it is very slick. Why is this 1, 0 and 0, 1? So you're seeing the same matrix that you saw in the last plot, right? Same covariance pattern, but a different distribution of the data. In the last one, it's a Gaussian blob. Everything is scattered. That was 1, 0, 0, 1. This is also 1, 0, 0, 1, but a different plus sign. Also 1, 0, 0, 1, but a different scattered signature. This is also 1, 0, 0, 1, different structure. Why is the last one 1, 0, 0, 1? Hmm. Yeah. 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 Hmm.
So how x varies within itself or y varies within itself.
Hmm.
Kind of limited in some sense. They are independent.
Hmm.
They can do whatever they want independently. However, the structure within each individual is kind of restricted by that one.
Fair enough. Good. Very good. That's all very, very good. That's correct. So if I were to, for example, like, I can ask you that if I were to hide this, right? How would you tell me what is going on along these diagonals? Along these diagonals, you can figure out. It's not very hard. But in some sense, is y even predictable from x? Is the information that is captured here, right? Like, so look at this here, right? So if x, for example, is going in this direction, your y can be either coming from here or could be coming from here, and that's why this is 0, 0, right? So for example, if I take this point here, I get one y value, but if I take the same x's, if I go and take an x value here, it's now predicting my value to be this to be my corresponding y, right? So for each observation that I'm doing, there are 2 points. That's why the amount that you measure in your x-axis does not tell you what is your y, and that's why those diagonals are 0, 0. Okay, is that clear? So the point of this is to show you that different distributions can have the same covariance matrix, but the information is in the covariance matrix, right? So why covariance matrix, right? Why are we talking suddenly about covariance matrix? Because what PCA does is PCA is rotating the covariance of your original data so that your final structure looks as close as this, in the sense that it is trying to maximize your variation along that particular axis. So in this case, I started from this covariance structure, and when I performed PCA, the axis that I got led me to see that along this direction I have slightly maximized my covariance, overall covariance, whereas in the other direction there's not much happening. That's the goal of PCA. Does that make sense? So how to start from a covariance matrix and come to this, we will see in just a bit, right? So this is a theorem, right? And I started by bashing theorems, but this is a good theorem. We will not go, of course, into the details, but what it says is very, very beautiful. It says that you can start from any rectangular matrix in which has all real values. It could be any dimension. It could be dimension is n cross m, right? So this is n rows and m columns. This is your matrix A. Anything inside, I can always decompose this in this format. Why is that format special? Because U is a orthonormal matrix. So if I multiply U transpose, I get a unit vector, a unit or a diagonal unit matrix. So in this matrix, all the entries along the diagonal are 1, everything else is 0. That's what I refers to. Similarly, your V transpose V is also I. So this is also orthogonal. But this is a diagonal matrix where it has values like sigma 1, sigma 2, sigma n, and everything else is 0. The reason it's so beautiful is you can do this for any real matrix, right? So you can, if you want to do, we will see what is the meaning of this in just a bit. But when you actually do this decomposition, the sigma 1 is higher than sigma 2, is higher than sigma 3, and so on. And this is a way to decompose your data so that you retain information. There is another theorem which will follow this, which will say that if you want to save space, right? This is, so let's look at the dimensions of these vectors, right? So this is n cross m. What will be the number of rows in U? Louder. N rows, m columns. What is the number of rows in U? N cross. Okay. Okay. But is it okay if I write it as n cross m for now? Okay. So if then S has to be what? M cross m. Okay. V has to be what? V transpose has to be what actually? We're talking about V transpose right now. So n cross m, we'll talk about what is the actual number here in just a bit. This is the decomposition that you're getting, right? So you're taking a matrix which is n rows, m columns, you're decomposing this in other 3 matrices, right? What is the point of this, right? Like, why should I do this? N cross m, again, I'm retaining n cross m, and then m cross m, and then why should I even care about this decomposition at all? The reason we should care about this decomposition is we can actually save space, and we can do this calculations really quick once I show you the second theorem. But overall, here what these sigma, which is this matrix, is called is the singular values of your matrix M. That is your sigma. And in some ways, you can save space by figuring out what is the structure of this matrix, right? So sigma 1 in principle can be anything. These are always greater than equal to 0, but they could also be equal to 0, right? And that is where the magic happens. But overall, this is some black box logic where you can decompose your matrix. Now, what is the interesting part here, right? So overall, what your matrix is doing is in this singular value decomposition, you're taking a big matrix, which is, I've reversed the orders here, m cross n, doesn't matter. It is decomposing your U matrix into a m cross m, a sigma into m cross n, and a V transpose into n cross n, right? The second column of the number of columns here, you can ignore that part. It doesn't matter for this class. But overall, what you're trying to do is you're ensuring that this is a orthonormal matrix, and this is a diagonal matrix, right? So that's what this particular tries to show, that you only have values in here, okay, overall. So when we did it here, we switched certain numbers, and that column for this class does not matter what is the actual matrix. It will stop mattering even when I show you the next theorem. But before we do that, it's time for a song.
It had to be you. You D transpose V. I looked all around and finally found the SVD. Singular vectors in V and U. Orthonormal to singular values in D, positively made just for me and you. Dimension 16 might never be seen, but to decompose, everyone knows there's a matrix routine. Thanks to all this you can do, find the matrix of rank 2. It had to be you, D transpose V, the SVD. It had to be you, D transpose V, the wonderful SVD.
The singular value decomposition, or SVD, is one of the most useful results in matrix algebra, with a vast range of applications in applied statistics, especially useful in dimension reduction. Any rectangular matrix P can be decomposed as the product of three matrices of simple structure, U, D, transpose V, where U and V are matrices of orthonormal singular vectors, and D is a diagonal matrix of positive singular values in ascending order. Suppose that a matrix P has the following SVD. In a low rank, for example, rank 2, least squares matrix approximation is easily obtained from the first two singular vectors of U and V and the two corresponding singular values. This result allows data matrices of high dimensionality to be approximated optimally by one of rank 2, so that the data can be visualized in a two-dimensional space for easy interpretation. As shown by this map of countries, in terms of their attitudes about whether mothers should work outside the home or not.
So it's a good stopping point. Well, not for the lecture, but for the video. Does that make sense? But there's an important information that's missing as to why should those two dimensions matter, right? Like, so the video starts by motivating that you can decompose any matrix into this form. But why does it work actually? Like, what is that magic which allows it to go from higher dimension to lower dimension? We will cover this very quickly, and hopefully all of it will make sense, right? So when you think about any matrix multiplication, right, it's very hard. It's very hard because it's one of those things which requires innovations, right? So GPUs, for example, are innovations to do this kind of application or do this kind of multiplication very fast. So in some sense, it's a very cumbersome and a very difficult operation, or very time consuming, not difficult necessarily, but a time consuming operation. But what happens, right? Like when you multiply a matrix, what is it intuitively that is happening, right? You can see that I multiply these two matrices, and I can take this row and multiply it here, and take this row and multiply it here, and so on. But intuitively, right, like if you were to visualize it, what is really happening? So if I take these two vectors, which represent my R2 space, like real number space, 2 dimensions, when I multiply this by a matrix M, what is the operation that's happening? It's going to stretch these vectors. I'm going to still stay in 2 dimensions, but the way it's going to stretch these vectors depends on what quantity you have in M. Intuitively, when you multiply a vector by a matrix, this is the stretching operation that happens, right? So if I take these two vectors and I take a matrix and I multiply this, it will stretch in some random directions depending on what values you have here. Intuitively, that is what a matrix and a vector multiplication does. Stretch and rotate overall, right? So this vector, which was orthonormal, it got stretched here, and got somewhat rotated overall. That's the overall operation that happens, right? In case of SVD, that matrix M can be represented as U sigma V transpose. And how are the operations happening? So when the same matrix that you're multiplying, if I were to do the same multiplication with this decomposed version, the first thing that you're doing is you're keeping the orthonormality, right? So I'm just going to rotate this. When I multiply it by V transpose, it's just rotating. And then when I multiply this with sigma, that's where the stretching happens. So this got stretched because of the values that you have in sigma, right? So if this makes somewhat sense, you will see what is happening. This is where the information about which direction or how much to stretch or where to capture the variance is coming from. And finally, you do another matrix multiplication. This is orthonormal, so the direction, this kind of stuff will be fixed, but all that is going to happen is you're going to perform just a rotation overall, right? So the angle will not change. The reason these angles change is because of the values that are there in this sigma matrix. Does that make somewhat intuitive sense overall? So it's just a matrix rotation in this case. So very simply, if you have a matrix like M, like this, you can calculate the SVD. We'll do this very, very quick. There are 3 non-zero singular values here, right? So for example, if you do, this is a 4 cross 5 matrix. My dimension for U is 4 cross 4. My sigma is also 4 cross 5, and my V is 5 cross 5. Here I have 3 non-zero singular values, right? This is 3, root 5, and 2. They are arranged in descending order. 3 is large, then root 5, and then 2. The rank of this matrix is 3, basically because, well, the rank is the number of independent vectors, column vectors that you have, and you can see that this vector here and this vector here are basically same, or there is redundancy because this is a 0 vector, and this vector is 0 vector, and this vector are essentially the same. So the dimensionality of this is not 5, it's lower rank matrix because you can capture the same amount of information in a lower dimension. So this is 3. So if I wanted to save space and if I wanted to visualize this in 2 dimensions, I could just retain the first 3 or the first 2 components and visualize it. And that's what we are going to do today. Right? So what are singular values, right? So singular values are what is helping you stretch these, make these ellipsoids. So when you multiply this, you get these stretch vectors. This singular value sigma 1 is a measure of how much stretching is happening, which is that particular axis along which the stretch is maximum. That is your first singular value. And sigma 2 is the second axis where your ellipsoid has the principal axis and the sub-principal axis of that ellipsoid. Intuitively, that is what your singular values are. These are non-zero, right? So they are helping you stretch. When you do this transformation, they're helping you stretch this particular vector. Even it's fine if none of this is making intuitive sense, we will do an exercise and all of it will start to sort of show up, right? So how does that magic of only retaining the 2 rows or 3 rows or 4 rows work? That's because of this theorem, which is called the Eckhart-Young theorem. We will of course not prove it, but what it says is if you have a matrix M where you decompose this as U sigma V transpose, I can represent a lower rank matrix. So if I start from this big matrix, I can reduce it to this matrix, right? One way to do this is I can randomly throw any columns off, right? And it's okay, I can do it, right? I can take any two dimensions and I can visualize it. But what Young-Eckhart theorem says that if you really want to do this reduction operation from 5, let's say I want to reduce to 3, do the SVD first and retain the first R or X or K singular values. And that's how you get the best R rank approximation of your matrix. How that happens, why it works, we will not cover it, but that's what basically the idea behind SVD is. Does that make sense? So that is how the dimensionality reduction works in the SVD case. You take SVD of a matrix, which will decompose it into U sigma V. You take the first 3, 4, 5, whatever you want number of singular values, and you do this operation again, right? And we will do this again in the class right now. The reason we are able to retain this information is because of this sigma matrix. That sigma matrix has sigma 1 to be greater than or equal to sigma 2, greater than or equal to sigma 3, and so on. And this is how much information is there in your ellipses. This is a measure of how much spread, right? So the first diagram that I had drawn here, this is your sigma 1, this is your sigma 2. And that's how you are able to retain as much information as possible. Okay? Make sense? Yeah. Can we know the value of the dimension from the rank? So the rank is basically the kind of your still higher dimensional representation of your data, right? So in this case, the initial rank was 5 because that's your maximum number of columns. But you figured out from the columns that there is redundancy. So you said the rank of the matrix is 3. So I still have 3 dimensions to represent, right? So I can choose those 3 dimensions. For this, you don't need SVD, right? I could figure out from this which columns are redundant. I could have just thrown them out. The goal here is among those 3 dimensions, if I wanted to do it in 2 dimensions, which 2 should I retain? Which is more, where is more information, right? Is there an alternate representation where those 3, right? So what are those 3 actually? Those 3 are still, this is 1, this is 2, and gamma z. Those are your 3, okay? But I only want to represent it in 2. So I'm going to say, let me borrow some information from 1, 2, 3, make it principal component 1. Principal component 2, again, borrow some information from 1, 2, 3, make it principal component 2. And reduce those 3 dimensions to a 2-dimensional representation. We are losing data, yeah. We are doing this at the cost of, but we are losing data very smartly, right? We are saying that if I want to reconstruct the original data, I can do it. I will do it with some error, but I'm able to do it, right? So we will see how much data we lose overall, right? Okay, any other questions? No. Reduction due to rank, we are not losing information, right? Yeah. Exactly, right? So rank, of course, that's a matrix operation where you're just trying to figure out that, okay, how much redundancy is there in your matrix, right? So yeah, in the matrix representation. Now the second step that I'm doing is I'm saying that I don't even want that. Like, can I do better? Can I just do it in 2 dimensions? Okay, so there is one more thing, which is eigen decomposition. There are a lot of terms here, but a lot of it will just join together and will start to make sense. So when I say the SVD, the reason it's magic is because it works on any matrix, any real matrix n cross m. The matrix for eigen decomposition has to be a square matrix, right? So there are a lot of decompositions: singular value decomposition, and then eigen decomposition. We'll see what is eigen here in just a bit. But this is another way to represent your matrix. Here, A is a square matrix, and you can represent this in the form of PDP inverse, right? Where P is again an orthonormal matrix, and D is this diagonal matrix. Again, sigma 1 is greater than or equal to sigma 2, greater than or equal to sigma 3. This is again a diagonal matrix. I can decompose again any n by n square matrix in this form. I cannot do this without some magic, you cannot do an SVD. You can of course run an SVD also on this matrix, but you cannot do a principal component. You cannot do an eigen decomposition on a non-square matrix. You can do it only on square matrices. So here, this is where Shordeep's thing about eigenvalue comes in, right? So what are these matrices? This P that you're measuring here in terms of this matrix is an eigenvector. What is an eigenvector? An eigenvector is very simply the vector. So a matrix, when I multiply it with P that you have seen now, is just a rotation operation, right? So here, when I multiplied this with matrix, there is a rotation operation. What is very special about eigenvectors is the original orientation is retained. It just gets scaled, right? So for example, if this was your original, this is your P, which I am claiming to be an eigenvector, right? So this is P1 and P2. If this is your eigenvector, when I multiply this with my matrix, I will still get this. However, it would have gotten scaled by some factor. That is your lambda factor. So matrix multiplication by a vector is just a stretching, is just a rotation operation. In this case, that rotation is, you retain the orientation, right? So lambda P means that it's the vector in the same direction, but scaled by a factor of lambda. Okay, is that clear? Okay, right. So why all does this matter? Well, this matters because we can use eigen decomposition to calculate also a lower representation, lower dimensional representation of this data. So when we calculated the SVD, what we did not get access to is how much information am I retaining. That information, if I let's represent 2-dimension, there's no quantitative way that we can quantify. That's where the principal component analysis comes into picture. Is it says that I can reduce the dimensional dimension of your data to 2 or 3 or 5, whatever X dimensions, such that you retain X% of your information, which is quantified in terms of the variance that you capture. Okay, so very quickly, if M is your matrix, we can always decompose this in this form, right? What does PCA do? So PCA is something which you can only run on square matrices, right? So let's, for now, just follow me and say that, okay, if I do M transpose M, what will I get? This is N cross N, right? What will be this matrix? Huh? Sorry, what? So this is, but finally this is M cross M, right? Okay, okay. I was like, okay, anyway, doesn't matter. So, okay, what is this equivalent to? If you do this operation, so the way to open this matrix is, when you open this matrix, I did not do a transpose here because this is a diagonal matrix, and the diagonal matrix transpose is the same, right? Okay, what is this? This is I. This is, right? So a principal component analysis, right? A principal component analysis, if I do, this is a square matrix, I can do a principal component. Correct. Yes, sorry. Yes, thank you. V sigma square V transpose, correct. So V, as you remember, is the right singular values of M, right? And you've retained that V right singular value. So in a way, this is the basis on which you are representing all your data. Okay. Now, when you do a PCA on the square matrix, you can always do a PCA on this square matrix, right? So if you were to do a PCA on this, right? If you were to do an eigen decomposition on this matrix, right? This is basically equivalent to writing this in this form, right? P D P inverse, correct? That is the definition of an eigen decomposition. That eigen decomposition of a square matrix means that I can write it in this form, which means that my D is sigma square and my P is V. since V transpose V is I can write V transpose as V inverse. Very simple, right? No, even if you don't know matrix algebra, I think this is very intuitive. So what does it mean, right? So it means that the eigen decomposition, what is this matrix actually? It's a square matrix, but if I were to tell you that the mean of this matrix is 0, so each column mean is 0, what does this, what are you measuring when you do M transpose M? Okay, let's close. This is the formula for covariance, right? So when you do M transpose M, we have access to what? If this was, if I had already removed the mean, which means this is 0, this is 0. Is it a measure of covariance? It is a measure of covariance, right? Like I've already removed the mean, I've subtracted the mean from there. So this is what? Your covariance matrix. You can of course ask me why did I do M transpose M and MM transpose, and I will leave that as an exercise. You can do the same thing with MM transpose as well. We normalized it, right? So I'm going to talk about it. We normalize it by what's called scaling operation. We removed the mean, right? So in all these cases, your M should be, so let me talk about the recipe, right? So you'll scale the data first, right? You scale the data with a matrix so that each of your variable, the mean of that variable, right? So if you have, let's say, variable X and variable Y, their mean should be 0, right? So their mean, this is called mean centering. In your scaling operation in your scikit-learn or whatever package you use, that's what this particular operation does. Scale so that, so excuse me, this is center, sorry, not scale. This is centering, so you're mean centering the data, right? So when you run your scale function or whatever function it's called in scikit-learn, I don't remember, but this is what it does. So the centering will put the mean of all the variables to 0. After this, you can calculate this. This is a measure of your covariance. In other words, the eigen decomposition of the covariance matrix is equivalent to doing a singular decomposition of your original matrix. Okay? This is SVD. This is PCA. PCA is nothing fancy, right? It's just the SVD of your the eigenvalues of the PCA in this case, right? So sigma square is what? Is the square of that sigma, which means the eigenvalue. These are your eigenvalues, correct? D is sigma square. So your eigenvalues are nothing but square of your singular values of M, and this is eigenvalue of M transpose M. Does that make sense? So doing PCA on the covariance matrix is equivalent to doing a singular value decomposition to some extent or at your original matrix. Now once you do this, right, so once you calculate, you can do this particular recipe, you can start with this matrix, you can do the SVD decomposition, you can calculate your V is the set of eigenvectors that you're actually looking for. So this dimension V not only summarizes your singular values, but it actually is the eigenvectors of your original matrix, right? This is what you're getting from here. This is the same V. Right singular values, eigenvectors. Right singular values are the same eigenvectors of your data. So if you want to do a PCA, right, principal component analysis, it is, you can truncate this matrix to K dimensions, which will tell you that the information there is maximized. You can capture for when you get these, when you get the eigenvalue vector, how much amount of information you have captured is the total amount of information or the total amount of variance that you have in your data is nothing but summation of your eigenvalues. Okay, we will not do the proof, but when you do the PCA or when you do the eigen decomposition of any matrix, how much amount of variation you have in your data is captured in your summation of your eigenvalues. Now, if I decide to retain only two of them, right, that is the amount of reconstruction error that that is the amount of variance that I'm going to retain in my data, and that's what hopefully answers your question, right? So that is where you make the choice that how much should I retain. Well, if you retain everything, you get the same data, but just rotate it. But in this case, I cannot visualize it, so I retain only two because I want to visualize my data, right? So that's why you do this dimensionality operation. Yeah, it's a sorry. Yeah, thanks for clearing it up, right? So if I want to retain, for example, just one principal component, then the amount, this is the percentage of variance that your first principal component explains, right? And similarly, this is what your second principal component explains. The summation is the total variance explained by your data, right? So this will be a numeric value. This will be a percentage value, that how much percentage of information is captured along each of these axes. Clear? Okay. Lot of confused faces, right? Like, because it's just too much going on, right? Like, huh? No, it's mean centered, right? So you subtract the mean from each variable. X minus sigma, that X minus X bar, that's it. I will do it, right? So I can see it, right? It's so confusing, PCA, SVD, like I don't know what decomposition. But hopefully the first take home that I want you to take is, what is PCA doing, right? So PCA is finding out that linear space that will help you minimize the reconstruction error. That if I start from this point and I want to reconstruct my original data, I should be able to do it. I will, of course, occur some cost, but I'm okay with it because it's helping me come to lower dimensions. The second thing, which is equivalent, that is trying to do is, when I do this, when I figure out this hyperplane where I should put my data, right? Then along that hyperplane, the variance of this is maximized. Like, this variance is the highest possible variance that you can get, because that's what is the measure of your information. Okay, so I had shown this plot last time, but this is what the principal component axis is trying to find, right? So at each step, your vector is rotating. You're looking for what is the direction that you should keep. And once you see that, once it comes over here, that's when these red points would have spread the most. You can see that, well, hopefully you'll see it, that here is when they spread the most. That's what your variation is. There is a notebook here. There's a notebook actually on the course website which will allow you to replicate this. But I understand that, because it's not as easy to follow this. So what we are going to do very, very quickly is, on the course website, there are two notebooks. We will only be able to cover one today, actually. So this one is on the animation, how to reconstruct the animation thing that you showed. The lecture is not over yet. The main stuff is coming now. Okay. So the second one is maybe it will bleed through, and we will cover it in the next slide, in the next lecture. We will have time for that because the guest lecture is not for 1.5 hours. So I will cover the next example of actually applying this in the next class. But what I did is I created a very simple version to help you understand from each step what is it that happens, right? When you run a PCA, what happens, right? So this also notebook is available on the website. You are welcome to see it, right? So the first thing that I'm doing is I'm just creating two data sets, okay? So I will just show you what the data looks like. Right, so I'm just creating this random data set. Y is a function of x. There is Gaussian noise, of course, everywhere, and you can kind of see that principal component will fall from here, right? So that's what we are trying to do overall. We try to see step by step what is it that's happening in PCA. So step number 1, right? You can see this data goes from 0 to 150, right? So its mean will be around, for x will be around 50. This mean will be around 125. The first step that you do is very simple, is you subtract the mean from these values, so that your final mean is, this is your original data where I'm plotting where the mean value would look like, right? So this red point shows you where is the mean. I will take this value, I will subtract it from the x-axis, I will take the corresponding y value, subtract it from all the y values. At this point also, this is a linear operation. You can subtract whatever you want as long as it's a constant from your data. It's almost, it's just shifting this coordinate system, right? Visually, that is what is happening. You're just shifting it so that when I calculate this mean now, it will all be centered at 0. And let me show you what does that make sense, what we're doing? Step 1, put it in on center. So after I put it on center, this is what your mean would look like, right? So all you've done is shifted it so that when I calculate the mean now, the mean for x is also 0, the mean for y is also 0, right? You're subtracting two different values from x and y overall. Make sense? Everyone with me so far? Okay, right? Now I want to show you that there are two ways to do PCA. What am I looking for? I'm looking for what is that axis that I should represent this data. Principal component 1, principal component 2, for this data, what does it look like, right? There are two ways to do it. One, in R, you can calculate, you can either do the eigen decomposition of your matrix, or you can actually calculate the SVD of your original matrix, and both of them are will end up will give you very similar, well, same output. Okay. So here in the first part of the code, what I'm doing is I'm creating the covariance matrix. I'm taking the centered matrix M, calculating the covariance matrix using using the cov function. Why? Because when I want to calculate the PCA, I want to do the eigen decomposition on the covariance matrix. Why covariance, right? Why did I talk about covariance? Because that is what your measure of the data is, right? So whether this spread is more here, that is captured in your covariance matrix, right? So the eigen decomposition happens on your covariance matrix. So let me run this to show you overall what does it look like, right? So this is your covariance matrix, right? So along the x, my variance is 1462. Along y, it's 3366. And of course, along x and y, it's 1271 and 1271, right? It's equal. Now, I can also understand how much amount of variation is explained by each of these data, right? So to calculate the total amount of variance explained, I do a very simple thing, which is I take the eigenvalues, right? The sum of the eigenvalues is the total variance in your data, right? So I can print it here. And of course, this number will be very much dependent on your data. I can also calculate for here, I can calculate, there are only two principal components because that's the maximum number of principal components you can calculate because this data is two-dimensional. Now, if I'm calculating two of these axes by doing the eigenvector decomposition, right? That is very simple because all I'm doing is I'm taking this covariance matrix and I'm literally pulling it through this function called eigen. And before you do that, you should always read about what does it do. It decomposes the function to give you the eigenvalues and the eigenvectors of any input that you give. Everyone with me so far? Any confusion? Anything that's not clear? It gives you it in descending order. Like it's the algorithm is written like that. Let me show you. So they are, I mean, in this case, of course, you could have gotten lucky also, but if you did it with higher dimension, you'll see that these are all sorted in descending orders, right? So you know which ones to pick. Okay, then I could also just calculate, right? Rather, if I did not want to do this eigen decomposition, I could simply calculate the SVD of the original matrix, right? So D is the singular value. So this is, look at what is D and look at what is your eigenvalues, right? And if I do this, there is a mistake. Anyone, what is the mistake? Okay, we'll come to the mistake in just a bit. Let me first run you through the example. So here I could also calculate my D matrix, which is my singular values, using this particular code function. I can calculate, finally, if I want to calculate the total amount of variance which is explained by each dimension, I could do this. Okay, we're going to calculate now. So there is a mistake at this step. I will talk about that mistake next time. There is a function, there is a scaling operation that requires to be done here in terms of, because I calculated the covariance matrix, there's a square root by n minus 1 factor which is missing. I will cover this in the next class. So that's the mistake. But let me run through you for what happens after this, right? So if I now draw what these vectors would look like, right? So I have the eigenvectors, right? So this is eigenvector 1, this is eigenvector 2. The eigenvector and the singular vector, right? The direction of your right singular value. So this is your right singular value of the SVD of the original matrix. This is V, and this is what your eigen vectors are, right? So they are exactly the same. This is not true for the covariance matrix calculation, because there's a square root n minus 1 function which we'll cover next time where it comes from. But here that's why I can visualize what does this vector look like. So this is what I'm doing here. I'm calculating overall what are my principal components x and y. So this is your mean, this is your PC1, this is your PC2. You can, if you want, I can also show you what does the projections look like, right? So this is how you will project your data. This was your original point, this is your axis, you project it here, and when you project these points here, this is the variance that you're calculating. So if you calculated the variance of these points, once they have been projected, it will be equal to your singular value, your eigenvalue 1. Right? So your eigenvalue 1 is a measure of variance in this direction. So if you calculated these projected points, calculated their variance by the variance formula, I will leave it that as an exercise. This will be exactly equal to your sigma, your lambda 1. Similarly, I could do the projection along this axis, which I'm not showing you here. The variance along that direction will be your value equal to your lambda 2. Okay, and finally, this is how your rotated data now looks like. PCA has simply rotated your data so that the variance along this direction is maximum and this direction is next. This direction captures around 83% of your variation, right? So, or 83% of your variation is captured along first axis, and this is what is captured along the second axis. The comparison, you can actually put them side by side, right? This is your original data. Nothing has changed. Like the points overall, their relative distribution has changed. This was your original direction of variation. Now in the principal component, these are your projected points, where this is what overall, this is your original points, but now visualized in the PC space, and this is what it looks like. So it's basically a rotation along this axis that you're able to visualize, such that the maximum, if I told you, for example, right, that only retain one axis, you would only show this one axis, and this variation that you're seeing in the y-axis would have disappeared, and that would give you a reduction in dimension by 1. You could also do, well, this is too long, right? Don't have to do this actually. In R, you could simply have done just PR comp and been able to visualize everything here, right? So this is what that shows, that if you run PR comp, it calculates your principal component analysis rather than having to do either eigen decomposition on the covariance matrix or doing the SVD on the original matrix. Just run PR comp and it gives you your PCA. Okay, we'll stop here. Next lecture, we will begin maybe with the guest lecture. I will finish the NFHS 5 analysis, and when we meet on Friday, we will go through our course review. Mid-sem syllabus will be everything covered to the last class. Last class is a review, so you will also get an assignment to do this. What happened? Too much? I see. Okay, fair enough. So you'll have an assignment. We will be due on it's supposed to be due on 10th September, but we will see. That one I'm open to sort of extend it.